So as I mentioned, adding solutes, especially dissolved solids, to water tends to have a strong effect on the electrical conductivity of the water. Now here's one case where we're not going to get into the dimensionality of electrical conductivity because it gets complex into electrical properties of physics, and that's just not somewhere that we want to go in the scope of this class. But the units for conductivity that we measure are in typically something like microsiemens per centimeter. And a Siemens is the same thing as the inverse of an ohm, or what's sometimes called a mho. So it's the inverse, the conductance is the inverse of resistance, and a microsiemen is a unit of conductance, and per centimeter tells you something about it being normalized to a particular geometry of what you're measuring the conductance of. Now this conductivity, this electrical conductivity that we can measure, will vary with the dissolved solids in the water, but unfortunately it also varies with temperature. Fortunately, the variation of conductivity with temperature is a pretty well-known relationship. So what we tend to do is normalize for temperature. So we have a temperature-corrected conductivity, or it's sometimes called the specific conductivity or specific conductance. And that means you are specific to the temperature that water is at. So the idea is you say, what would the conductivity of the water be if the water were at 25 degrees Celsius? What this does is it normalizes the variation in the conductivity to no longer be a function of the temperature. We've corrected for the effects of temperature. So the only variation we should have left in conductivity, and a temperature-corrected conductivity, should be due to the dissolved solids in the water. This is really important when you're reading a conductivity instrument. You want to make sure you're looking at the specific conductivity if you're trying to understand the concentration of a solid from that number, and not just the raw conductivity that is not temperature corrected. And we'll point that out in future labs when we start looking at these devices for measuring these properties. So this relationship between electrical conductivity and concentration gives us a way to measure the solute concentration with a fairly simple device that measures electrical conductivity. In our case, we can make a reasonable assumption that an increase of 1 milligram per liter of sodium chloride is going to increase the specific conductivity, the temperature-corrected conductivity, by 2 microsiemens per centimeter. Now I use that circa there, that's just Latin for saying about 2 microsiemens per centimeter. This does vary a little bit, but unless you're talking about really strange water chemistry in fresh waters, this is the kind of relationship that you're dealing with. Now what's kind of cool about the abstractness of dimensions is the units don't matter. And we know that 2 microsiemen per centimeter change is consistently tied to 1 milligrams per liter, no matter what conductivity we're talking about in the ranges of fresh waters that we're dealing with. That means we can treat microsiemens per centimeter dimensionally just like a concentration. We can say those two are just like each other, and therefore we can use that approximate equality to make a conversion from a measurement of conductivity to a measurement of concentration, just like we do a unit conversion using the unit factor method. And I will get to an example of that in just a minute. So even though those are very different units and on the surface appear to be very different dimensions, because those two are consistently related to each other, we can dimensionally treat a conductivity unit as if it were a concentration. I'll show you how that works in a minute.